Set it to record. Okay, questions on this one? Let's look at this one. Okay, so we look at this, and they want us to evaluate this integral. So, first question, is it undoing the chain rule? No. What small change could we make to this so it would be undoing the chain rule? So instead of changing something under the radical, so change something else besides changing the x squared plus 16 to make it undoing the chain rule. What would you need? Yeah. Multiply 5 by x. If you had an x in the numerator, would it be undoing the chain rule? Then it would. Then it would, because essentially x is essentially the derivative of x squared. So if you had 5x in the numerator, it'd be undoing the chain rule. That's not what we have. So we can think about doing a change of variables. And so let's chase that out quickly here. And so maybe we think u is, what, x, by the same logic as the last problem, x squared plus 16. Then we need dx. Okay, so what, x squared is u minus 16. X is the square root of u minus 16, actually like plus or minus. And then we need dx. So it's like 1/2 u minus 16 to the negative 1/2 du. Did it help? So if we rewrite this now, so the point is of doing this is that it's going to be something. The change of variable is going to make it better. It's going to make it something that we can do. So now we would have 5 over square root of u. That's nice, but our dx is 1/2. And now we have another radical u minus 16. It did make it better. So if I multiply these in now, I'd have the square root of u squared minus 16. Because they're both square roots, I can multiply those together. And I have the square root of u squared minus 16u. It's not any better than what we had in the first place. So this is how it goes sometimes. You have an idea, and you chase it out, and then you get something, and you think, well, that didn't really help me. It didn't make it better. So something else. Either I'm going to need a different substitution, a change of variables to start with, or some other technique. And so in this case, it's the latter. It's some other technique. So this is one of your table forms. So there should be a table entry like that. So that the common table forms are the x squared plus a squared, x squared minus a squared minus x squared. Those are very common table forms. So this one is, there should be a table that looks like this. 1 over square root of x squared plus a squared dx. And does anybody have what that would be? What is it? 77? Can anyone confirm that? Check that out. $77. Does it look exactly like what I wrote up here? And so with the table, here, if it's identical to what's in the table, then you can just write down the answer from the table. That's the point. They give you the antiderivative, and so we can just write it down. We just need to know what is our a squared. Our a squared is 16, which makes a 4. And then we also have the 5 to take care of, but that's no problem. So wherever there's an a, we're going to use 4. And then we also, ours is also multiplied by 5. So what is that equal to, Joseph, in table 77?
The natural log of x. Natural log over x plus the square root of a squared plus x squared.
Okay. That's the whole thing?
That's the whole thing.
All right, awesome. Okay, so we've got something just like that. It's just times 5, right? So if we put in 5 times natural log, and let's just do absolute value just to be sure, x plus square root of, what's our a squared? 16 plus x squared. Did I follow the formula correctly? X plus square root of 16, looks like I did. And we can preview it. Is that what we wanted? So that's the idea of tables. You just find the one that's similar and apply the answer. Okay? That's the idea of table integrals. So those were the two that had the lower success. So we'll stop there and then we'll go on to the next. Let's look at the next set. Number 6. So maybe 5 and 6. Let's look at 5. Okay, so there's some different things going on in this one. So the first thing is, if we're going from negative infinity to infinity, we can still do one limit. So we can rewrite this way. The limit as a approaches infinity, and then we'll just go from negative a to a. And that will have the same effect as this improper integral from negative infinity to infinity. So as a goes to infinity, the opposite of a goes to negative infinity, and that's what we want. Now, so our next issue is this antiderivative. Again, we have to figure out what technique we're going to use to do this. Okay? What would we need in the numerator for this to be undoing the chain rule? Undoing chain rule, in the numerator we'd need 9x to the 5th. And then it would be natural log, right? It would be natural log of 1 plus x to the 6th. If we had 9x to the 5th, then we could have we do natural log of 1 plus x to the 6th would be essentially, and then figure out the factors, would be essentially our antiderivative. Okay, we don't have that. Okay? So we have to kind of go through our bag of tricks to see what we've got that's going to work here. So undoing the product rule. Maybe, but we're going to, at the end, I'll show you again the common forms for undoing the product rule. It's maybe undoing the product rule, but it's still, I'm guessing that's not going to work, just from my experience. What else do we have? So notice this is 1 plus x to the 6th, which is kind of like, which is like this. It's 1 plus something squared, right? What squared is it? X cubed squared. Agree with that? And why did I do that? Because it works. I recognize that this is kind of like 1 plus something squared in the denominator, which is inverse tangent. And notice what's inside here. X cubed inside, and what do you have up there? X squared. So when I rewrite it this way, 1 plus x cubed squared, and I'm thinking inverse tangent, it is undoing the chain rule. Do you see that? That it is what's plugged in here, what's our interior function of inverse tangent, we have its derivative right there. So it is undoing the chain rule. Now, if you could also use a change of variables to help you with that if you wanted. If you did u equals x cubed, you could chase that out, and then you would get, in u, you would get 9 times, you get 9 over 1 plus u squared if you chase that out, and then that looks a lot like inverse tangent. But hopefully you can see that that's the derivative of arctangent with chain rule, with our interior function being x cubed and its derivative being essentially x squared. Okay, so we've got the tangent inverse of x cubed. And so we have to clean up the mess here. So if we were to take the derivative of that, would we get exactly that? We get 1 over that thing squared times 3x squared. We have 9x squared. So how do we change this so that if we took the derivative of it, we'd have 9x squared? We need another 3, right? We need another 3 out here, multiplied. Now the derivative of that is this one, by the undoing the chain rule. Okay, so hopefully you were getting faster at that, because undoing the chain rule, it keeps popping up in all these techniques. Hopefully we're getting better at that and we can get faster. That was the goal in the beginning. So now we got to evaluate this. From negative a to a, the inverse tangent of x cubed, which is the limit as a approaches infinity of the 3 inverse tangent of a cubed minus 3 inverse tangent of negative a cubed. Okay, well, what the heck is that? So we have to know something about tangent and inverse tangent to evaluate these limits. So if you remember, tangent is, one way to think of tangent is on the unit circle of an angle is the slope of the terminal side of the angle. So if you have, this is your angle, say theta, then tangent of theta equals the slope of that line, or like sine over cosine, the y coordinate divided by the x coordinate. So what happens to the slope when theta gets close to pi over 2? So as theta approaches pi over 2, tangent theta does what? What happens to the slope as we get closer and closer to being vertical? Tangent theta will approach, hopefully, so I'm not hearing, it's infinity, right? So that slope, as you get closer and closer to pi over 2 at the top of the circle here, just gets infinitely big. Gets as big as you'd like. Just get a little closer to pi over 2, and the slope's even larger. And so there's no limit to how large that slope gets as you get closer and closer to pi over 2. And likewise, negative pi over 2, if you go this way and you go to negative pi over 2, tangent theta approaches negative infinity. Okay, so by saying that we want the limit of the inverse tangent as a goes to infinity, So we're saying that this is then the inverse tangent, saying what angle is that going to be if we could ever get to infinity for the slope, right? So now for arctangent, this is like the slope, and the output is like the angle. So now we're gonna make our slope go as close. Let our slope get infinitely large, and the limiting angle of that is what? So we're going to let the slope get infinitely large, positive. That's here in the first quadrant. What angle are we essentially as our limiting value? Pi over 2. Okay? And now we're going to let the slope get infinitely large negative. That's what this input of arctangent is. It's the slope, and then the output's the angle. So we're going to let the slope get infinitely large negative. What does the angle, it's the limiting value of the angle when the slope gets infinitely large negative? Negative pi over 2. So that's what happens. So we have 3 pi over 2 minus negative 3 pi over 2. Which is 6 pi over 2? Or 3 pi? Did you catch it? Did all that explanation make sense? So that's reasoning through the understanding of tangent, and arctangent would be, or inverse tangent would be reversing what's going on. So basically, letting this input of inverse tangent get very, very large is like saying, what does the angle approach as the tangent gets very large? And then what does the tangent, so as the tangent gets very, very large negative, what does the angle approach? That would be the negative pi over 2. So then when we put those in, we get 3 pi. Questions on that one? Anybody? Okay, one more of these. Let's look at the last one. Really, this one? Okay, so improper integral, 1 over 3 halves dx. So this one is of the form that we could answer the question but without doing the math. Sometimes we have to do the math, but this one is, we talked about last time. It's of the form 1 over x to a power. And we showed at the end of class that, so this is basically 5 to infinity, 1 over x to the, this is like 1.5. So we looked at, in general, if it was 1 over x to the p, when would that converge and when would that diverge? Meaning, when would that thing be actually a finite value, and when would it not be a finite value? So what did we conclude? So it's convergent when what? We showed that it's convergent when p is greater than 1. So how about this integral? Is it going to be convergent or divergent? It's going to be convergent because our exponent there is greater than 1, but let's do the math. So we're going to do this antiderivative, which is, this is x to the minus 3 halves. So we're going to have negative 1 half. Negative 2 x to the minus 1 half is that antiderivative, which is negative 2 over square root of x. And it's going to be the limit as a goes to infinity. 2 over square root of x. As a goes, as we go from 5 to a. Yeah, probably, yeah. 2. Thank you. Negative. Thank you. Good so far? So that's an easy antiderivative. That's the power is negative 3 halves. We raise power to negative 1 half. We got our factor of negative 2. So we're going to do the limit as a goes to infinity of negative 2 over a, negative 2 over square root of a, plus 2 over square root of 5. And as a gets very, very large, what does this first term do? Goes to 0. As long, so for just a straight up limit, as long as the power, this is a to the 1 half, as long as that power is greater than 0, the limit will go to 0. Go to 0. So this is a to the 1 half. So when you have just a limit of 1 over a number to a power, all that power has to be is greater than 0 for that fraction to have a limiting value of 0. But for an integral to converge, it's 1 over x to the power. That power has to be greater than 1. Okay? So don't get that. So that's 2 little rules that you have to know. Right? So for the integral, that power has to be greater than 1. But just for a limit to be 0, that power has to be greater than 0. Any positive exponent in the denominator, taking the limit, will give you 0. So it looks like this is 2 radical 5, 2 over radical 5. Questions on this one? Okay. Any questions? So let me give you just a little concept quiz related to this stuff. How about this? No, you're not going to turn it in. So the question is this convergent or divergent? From 3 to infinity, 2x over x plus 1. Convergent or divergent? No. Convergent or divergent? This is a self-assessment quiz. Self-assessment. How many think it's just, so without doing a lot of math, how many think it's convergent? How many are not sure? It's okay. How many think it's divergent? How many think it's divergent? Lots of people think it's divergent. Why? But this, okay, so, but, you thinking 1 over x to the p? Is that, well, it doesn't really fit that form, right? This is a different, this is a rational function. It's not 1 over, doesn't really fit that form. So it's not 1 over x to the p. You can't, you might be able to write that, but it's not just as simple as, you know, p is not greater than 1, so it's divergent. You could kind of reason that. Let me sketch this graph. If you remember, if you were to sketch this graph right here. It would look like this. Okay, and this is our that graph, and y approaches 2 as x approaches infinity. So this levels off at 2. So I'm drawing you the graph of this function right here. And as x gets very, very large, y approaches 2. How many people think the integral is convergent? How many? Now we can know. Now we can know. How many people think the integral is divergent? So a few convergent and very few divergent. So this is a big deal that we talked about on Monday. That you got to get this. So why don't you talk? Take a minute. Talk to the person next to you. Without doing any math, is this a convergent integral or a divergent integral? We should know. We should know. Here's a hint. What kind of function is 2x over x plus 1 in this context? Okay, that's your hint. Keep talking. This goes back to week 1. Meaning of integral, meaning of fundamental theorem, which is crucial for your exam Friday. So to answer this question, is that convergent or divergent, you have to remind yourself, what kind of function is 2x over x plus 1 in this context of an integral? Go, keep talking. Okay, so let's answer that question. What kind of, or now let's ask, how many people think the integral is convergent? Oh, more people. How many people think it's divergent? We got some more divergent too. It's split. What kind of function is 2x over x plus 1? It's true it's a rational function, but in the context here, what kind of function is it? It's a rate of change function. It's a rate of change. And what does an integral mean? Remember? Okay, so when we sum up a bunch of little bits of change, we get what? The total change. The total change in the quantity starting at 3 until infinity. Okay? According to this rate of change. This rate of change. What is a rate of change? So eventually the rate of change is essentially 2. And it's going to get closer and closer to 2. So at some x value, it's pretty much indistinguishable from 2. And then it's 2 forever. The rate of change. And we're asking, what's the total amount of the quantity? What's the total amount of the quantity that you get starting at 3 to infinity, when essentially, eventually, the rate of change is just a constant of 2? How many people think the integral is convergent now? How many people think divergent? Okay, now we're getting there. What does a rate of change of 2 mean? It means every unit of x, what happens to our quantity? We go up by 2. Every unit for x, we go up 2. That's what the rate of change means. The quantity increases by 2. So eventually the rate just becomes 2. We're essentially close to 2. So what's happening to the quantity at infinity? You just keep adding 2. You just keep adding 2. You just keep adding 2. So this is clearly convergent or divergent? Divergent. It's divergent because this is the rate of change function. It's telling you that you're going to keep, essentially you keep adding 2 to your quantity for every value of x that goes by. And we're going to do that to infinity. So the quantity is just going to go up and up and up at a rate of 2. What's necessary for the rate function in order for these improper integrals to be convergent? What has to happen to these rate functions? They must do what? We talked about it Monday. That's why we're reviewing this. Rate functions must become eventually 0, or the sum of all the quantities that are adding up the quantity is never going to have a chance to converge. So our rate functions must look like this. Is that enough for convergent? The rate function the rate of change eventually becoming 0, or essentially very close to 0 for large x. Is that enough for it to converge? So it's necessary that it gets to 0, but then it also has to get to 0 fast enough. Okay, here's 2 rate functions. Here's 2 rate functions. Okay? Is it possible that if we were doing an integral of these rate functions, is it possible that one or both would converge? Is it possible? Yes, because they seem to be getting smaller, right? Which one has a greater chance? Purple one has a greater chance. It seems like it's getting to 0 faster. Uh-oh. Which one has a greater chance? I didn't show you enough, right? I tricked you, okay? So the red one actually has the better chance of being convergent. And I'll tell you that the red graph is 10 over x squared. And the purple graph is 1 over x. These are rate functions, right? So if we were to integrate, say starting from 15, 10 over x squared dx, and we were to integrate from 15 to infinity, 1 over x dx, they both have a chance to converge. They're both getting very, very small, the rate. Okay? But that's not enough. They need to get small enough, fast enough. Okay, so do they both converge? Do neither converge? Or does just one converge? Talk. Okay. The first one. So the first one is the red one, the red rate function. We said it has a better chance. Is it convergent or divergent? Convergent. That integral is a finite quantity. It's a total amount of a finite quantity. How do you know? P is greater than 1. So this is the red. So I'll circle in red. P is greater than 1. And it's getting very small. That rate's getting very, very small very fast. So in the long run, your rate is essentially 0. And it gets there fast enough so that the amount of your quantity levels off, right? You're just adding such a little amount at the end that it levels off and is a finite quantity. Only because the rate gets close to 0 and it gets close to 0 fast enough. The second one is the purple one. That also gets close to 0 if you make x large enough. Is this convergent or divergent? This one's divergent because P is not greater than 1. It's equal to 1, right? So it meets the necessary condition that the rate goes to 0, but it doesn't get there fast enough. You notice it's hovering higher. It doesn't get there fast enough. So even though the rate goes to 0, you're still adding on to the quantity, and it will never level off. It will just keep getting, the quantity will just keep getting greater and greater and greater, even though that rate goes to 0. So necessary that the rate function gets very close to 0, or the limit of the rate function value, the limit of the rate is 0. That's necessary, but it's not sufficient. What's sufficient is it's got to get there fast enough. So for these types of functions, the 1 over x to the p, we can just know that without doing the antiderivative and doing the math. We know that if that's your rate function and p is greater than 1, you get a finite amount of the total quantity, even if x is allowed to go to infinity. Okay? Other forms of rate functions, you have to do the math. You have to actually find the antiderivative, take your limits. If you get a number, you did all the math right, you get a number, then that's your conclusion that it's convergent. Okay? Now that would be for other types of functions whose rate function approach 0. Other rate functions that approach 0. If you have a rate function and it doesn't approach 0, you don't have to do any math. Like the very first one I gave you, right? It approached 2. So that rate was essentially becoming 2 in the end. That has no chance to converge because you eventually just keep adding 2 to your quantity. As x goes up 1, you keep adding 2 to your quantity. Okay, hopefully that's better. But this is a really important principle to understand these improper integrals. Okay, let's just quickly, so again, your exam. You have review materials. I do want to do one more thing. So in exam prep and homework solutions, you've got all this stuff. You've got the Review outline. This is should be the centerpiece of your studying, okay? There's nothing on the exam that's not highlighted here. That first week, week and a half of the meaning of integral, meaning of fundamental theorem, crucially important. Go back and watch those videos, review that stuff. That is definitely a big part of the exam. Then certainly, we learn these different techniques. In a moment, I'm going to just run through really fast kind of how you might identify the different types. And then what we talked about in improper integrals. Okay, so, and then I've got some solutions. Remember on the front of your exam, this is what's going to be on the front cover. Okay, this means you're going to fill this out, fill out all the identities before you start. Take a minute, 2 minutes to do that, and you get a bonus point on the test, and then you'll have all the formulas. Okay? You will need a scientific calculator for the exam. Something that just does basic scientific math. Bring a calculator, okay? It's partially multiple choice and partially free response. There's both. There's both multiple choice and free response on the exam. Is that the yeah? What? Yeah, sure.
So when you say we need a scientific one, you're not using that?
No, you can use a graphing calculator. That's fine. But just as long, minimum requirement is scientific. Yeah. Don't pack up. Don't pack up.
The table forms, like the radical x squared and x squared stuff, will those be?
Yeah. If there's a table integral on the exam, I have to give you some list of table formulas. That's the point. You have to have that to do those problems. Okay, and then there's these practice problems. Notice here, there's this list here. From the practice problems, you're not responsible for those. But anything that's not those on this practice integral sheet would be kind of fair game for the type of things on the exam. So this is the idea that these are all mixed up now. These are all mixed up. So your first, just quickly, your first attack plan is it undoing the chain rule? Okay, question. What do you mean? So if you have recitation today, you're going to do some review. If you have recitation on Fridays, you're getting an optional review. And then, no, there's not. That's it. And then all office hours tomorrow. So you got a whole day of office hours tomorrow. Okay. All right. So identifying these. So you look for undoing the chain rule. If it's not that, the trig ones are self-explanatory, right? The trig ones just should, if they're trig functions, right? So that's easy to identify. Undoing the product, I gave you a list when we did undoing the product of common forms for undoing the product. So let me just point those out. Natural log and natural log times x, like t to the something. So that's going to be undoing product. This is also going to be undoing product. Z times exponential function, or x times an exponential function, or x times, these are all, the ones I'm circling here, are all undoing product rule. Common forms for those. Arc sine and arc tangent are undoing product rule. Okay? Something like this is going to be change of variable. It's not undoing the chain. It's not done. That's going to be change of variables. That's you're gonna do a u equals 5 plus x. Change of variables. Okay, partial fractions should be obvious. A rational function, partial fractions. So the blue ones are partial fractions. That red one is change of variables. The black ones are undoing product. The ones that have lots of complicated trig formulas, obviously those are our trig integrals. So you have to have, so this is what this sheet is for, so you can have some practice of just coming to any integral, because that's what the test will be like, and being able to not only apply the techniques, but pick the right technique, or eventually get to the right technique to do it.